Okay, last couple of days, mainly yesterday, I wanted to focus on square root graphs. So those are radical graphs. The point I was trying to make, that I hopefully did make well, these graphs that we're working on in this non-polynomial function unit, they're all going to look very different. Like, there's not a lot of uniformity to them, and it's going to get much worse today. If you've looked through the notes at all, like, kind of scan through the next couple of pages, all we're going to do is graph a whole bunch of different graphs. And I just want to show you a ton of examples of how these graphs can look. Does that make sense at all? So, like, there's not really as much like skills to this. Typically, the question I'm going to ask you is graph this graph, and usually I'll ask you tell me the domain and range. That's like a typical question to answer. Okay, so, yeah. So I'm going to show you basically a whole bunch of weird and odd-looking graphs that are considered to be rational. Okay. First thing to start with then, do you guys remember the definition of rational from last year? Rational, basically another word for fraction. So we're going to deal with a lot of things that are fractions today. If I were to give you this rational expression right here, there's one number that x can't be.
0, negative 2.
Yes.
Sorry.
We'll get there. Does everyone get why negative 2 is not a valid answer for x? You can't divide by 0, right? And minus 2 plus 2 would make the denominator 0. So that's going to be one of the things we're going to consider a lot when we talk about domain and range. Previously, I told you guys domain and range were often basically everything, right? Element of the reals. But whenever we do rational functions and radical functions, there's often numbers that we can't use. Like when we do radical functions, which are square roots, you can't square root negatives. Does that make sense? And here when we do rational functions, you can't let the bottom of fractions be equal to 0. So, I want to start off by just kind of reviewing some stuff that we've done that's similar to this. If I were to give you two functions, like say x squared plus 6x plus 9, a second function of x plus 3, what does this notation here mean? Okay, so divide them basically. So it would be equal to x squared plus 6x plus 9 divided by x plus 3. Sometimes, in our first unit, these things actually do divide by each other nicely. Do you guys remember how to factor the top? What would the top factor to? Okay, so you could write this guy as x plus 3 over x plus 3. And you could cancel a set of x plus 3s. So sometimes these things, they do divide nice and evenly. That's fantastic. But to be honest with you, that's kind of rare. It's almost going to be luck if it happens. For example, this set of functions right here, this one would be x squared plus 5x plus 6 over x plus 4. The top actually doesn't even factor, I don't think. Because you're looking for numbers that add to give 5 and times to give 6. Well, yeah, they do.
Oh, negative 3.
They do, yeah, okay, so it does factor, x plus 3, x plus 2. But does anything actually cancel?
No.
Okay.
So is it worth our time to factor if that will cancel?
It's always worth it to check.
Okay, so you should factor.
Yeah, because if it does factor and it does cancel, it's not really a rational function anymore. Now it's back to a polynomial function, which was our first unit. Does that make sense? Because like this graph right here, we could graph the graph of y equals x plus 3.
Yeah.
Right? This graph right here, though, my goal today is to explore what the heck does this graph look like. And hopefully at this point is going to be made clear. These graphs look weird and stupid, and they're going to be all over the place. Okay, be forewarned. Okay. Like if you want to, let's start by graphing this one right here just to see what it would look like. So if you want to type this in properly, you're going to want to make sure you use brackets. So do like big bracket, x squared plus 5x plus 6, close bracket, divide by new bracket, x plus 4. Hello? Or no? Okay. Kid just steps in.
What? Oh, mine doesn't look like that. Mine looks like that. What does yours look like?
Okay, depends on which calculator you have. Some calculators will draw a vertical line straight up and down here.
Oh, that's the thing.
Yeah, that's called an asymptote, which we learned about last year a little bit. I'll reference that a little bit later, but does everyone have a graph that if you ignore this line straight up and down looks something like this? Okay, weird looking graphs. Okay, they're all going to be kind of weird in their own right. Okay. So, one thing I do want to remind you of in the first unit, though, let's say they do actually divide evenly. Then sometimes you get what's called that hole in a graph. You guys remember that concept? Here, if I give you x squared minus 1 over x minus 1, you could actually FOIL it out to like x plus 1, x minus 1. And if something cancels, that's fantastic. It makes it like a linear graph, but there is a hole in the graph at 1. Does that make sense? Because 1 was the number that you weren't able to actually use. How would you find the y value for the hole in the graph? Do you guys remember how to do that? Well, you can't actually put a 1 into the original function, so you put 1 into the function after you've canceled. So the remainder would be like x plus 1. So then now you can put in 1, and then y would equal 2. Which means that the hole in the graph was at 1, 2. Okay, so if the graphs do evenly divide them properly, okay, then the one number that you can't use is where x is 1. Does that make sense? Because 1 minus 1 on the bottom would be 0. Well, you can't plug 1 into this graph right here, and you can't plug 1 into this graph right here. But if you cancel the problem, now you can actually plug 1 in for x. And that'll tell you where the hole in the graph is for y.
Okay.
Does that make sense? Colin?
So, really plug in into x value and what you get is your y value.
That being said, though, neither of those values can exist, though, because that's where the hole is.
Right.
Does that make sense? So the hole is here at 1, 2. So you could say your domain is everything you want except 1, and your range is everything you could want except 2. Okay. So we have done this a bit before, but now let's just do a whole bunch of examples. Let's skip this one here. Let's just move on. Well, no, let's not skip. I think you guys get the point I have here, though. We're going to now do functions, and they won't always divide evenly. Sorry, go ahead, Colin.
I was just wondering, on the last problem, how did we get 1?
Because x minus 1 on the bottom means that the one number you can't plug there is 1, because 1 minus 1 would give you... Yeah. Okay. Here's an example of a rational function that hopefully you get my point. Sometimes it does cancel. Like, the work here, it factored the top, I factored the bottom. Sometimes something cancels, but like not everything cancels. And so there's like a whole bunch of possibilities. There's the possibility that nothing cancels at all. There's the possibility that something cancels. There's the possibility that some things cancel but other things don't cancel. Long story short, each question is going to be kind of unique, okay? So let's do a whole bunch of examples. First example, let's sketch this graph and talk about what the heck is happening. So the graph is 1 divided by x. So grab your calculators. One divided by x.
Wait, we've seen those before.
We've done this one last year, actually. I wanted to start with one that we know. This is a lot similar to a topic we did in chemistry as well. It's called an inverse relationship. As something goes up, the other one has to go down. You guys remember that topic at all?
Yes.
It was in the gases unit in chemistry. It was Boyle's law. If pressure goes up, volume goes down. As x goes up in this graph, y goes down. That makes sense? So we've actually seen this graph before. So if you were sketching it out, it looks roughly like this. Oh, thank you. I'm totally wrong.
Same idea.
Yeah, same idea, just, not this. Yeah. Okay, so like this. And this. Okay. Do you guys remember this term at all? The term is called asymptote.
That's when they don't.
Okay, an asymptote, the definition of an asymptote is a line that the graph can never touch. Basically, it's like what value for x does it never reach? 0, yeah. You'd say that this graph right here, it gets really close to 0, but it never actually gets to be 0.
Y and x.
Actually, in this example, it's for both y and x. In this direction here,
Don't give that.
do you want to do it again? All right, go for it.
Hello? Yeah.
Okay. Do you guys remember the convention for how we draw asymptotes at all?
This is like a lot.
It's usually it's a dotted line. Yeah.
Oh.
So like
Okay.
you could draw like a dotted line right here, meaning that this graph will never have the value x equaling 0. And this particular graph also has a dotted line going this way, meaning that y can never be 0 either.
I know.
Yeah,
I
that's
was like,
a
wow,
lot.
you are so good.
It's
No,
really
no, no.
not
It's
that-
like
Yeah.
Whoa.
And then
Talent.
I had to watch it 10 because I was like, there's no way he's that good.
what if I were?
No.
All right. Does this sound familiar to you guys? We've done this one in the past.
Yes. Yes.
I don't remember the dotted line thing, but I meant.
Okay. Your calculators, depending on which brand of calculator you have for like TI-83, 4, 4 plus, color one, sometimes your calculator will actually draw in the asymptote for you. So you have to like know whether your calculator does it or not. That first graph that I did, my calculator does draw asymptotes. You don't see this asymptote though because it's going right on top of the x-axis. Okay, so you just need to know what your calculator does. Let's try another one. X plus 3 to the power of minus 1. You guys remember what power of minus 1 means?
It'd be 1 over x plus.
It means 1 over x plus 3.
I don't remember how it looks, but
Okay, well, let's graph it. I mean, that's why we're going to use our calculator for everything today for this reason.
good.
Now, don't type it in like I have typed in right now. Why not?
Because it would be like 1.
Divided by x and add 3.
Okay, so in terms of brackets, we need it to be x plus 3 all on the bottom.
Oh, it's the same thing, but.
Yeah, definitely.
Okay, now your graph may look somewhat similar to mine. Do you guys see how mine draws the asymptote in? It's at negative 3. Why is it at negative 3? Well, here's a couple of reasons. X plus 3 has, x has now been replaced with x plus 3. Plus 3 moves the graph 3 units that way, left, yeah. Another way of looking at it is, what number for x can you not use? Negative 3. Well, that's your asymptote. X can, usually we write asymptotes as x can't equal a number. I don't care whether you write it with the can't equal sign or the does equal sign. It doesn't matter to me.
And then 0 for y.
Good, yeah, y still can't be 0 though. So the graph looks like this and that. Here, I'll even draw the asymptote in my hand. Other things you could do to double check in your calculator, you could go second table, take a look and see what happens, and you'll notice here minus 3 has an error. That's a good indicator that it's an asymptote.
They do that for y equals 0.
You can't really do it for y equals 0. There's no way of really solving for what an asymptote is in the y direction that's really useful. Usually you have to look at the graph and kind of figure out what it looks like it's getting close to. You could kind of look at all your y values and say, look, as the x values get higher, see how all these y values get smaller and smaller. If that makes sense. But it's never actually getting to 0. Like we're down to 0.03, 0.02. So I can't really prove it the same way, but you can use the same logic.
Is it the same for y all the time? Like, is y
Nope.
always 0?
No, I'm going to give you different examples there too.
Okay.
For sure, I'll tell you that it's not always that. So far, so good? Oh, you know what I've been skipping? Domain and range. But hopefully you guys have that so far. The domain of this graph would be x as an element of the reals, but x can't be negative 3. Can't be your asymptote.
Do we have
Sure. If you want to take that off, you can. I'm fine with that.
But what?
Like the x is the element of the reals part.
Oh, you don't want that.
If you just want to tell me x is everything that you want it to be, but not negative 3, I'm fine with that. Okay.
So wait, that can go for your.
I guess your asymptotes would be your domain and range then, wouldn't they? Does that make sense? Okay. By the way, that's not always true. Your asymptotes are not always your domain and range. Okay, let's try a new one. This one's kind of different. 4x minus 5 is on the top of the fraction, and x minus 2 is on the bottom. I get something that looks roughly like this.
Yeah.
Okay, so let's talk about what happened on this particular graph. First, let's talk about domain. There's one number in x that you can't use. 2. Does that make sense? The one number you can't plug in is 2 because if you try to do 2 minus 2, the bottom of the fraction would be 0. So let me just sketch this guy real quick here. It looks roughly, ooh, that was ugly, like this. That was close. We'll go with that. So the one number for x that we can't use, x can't be 2. Okay, that being said, y can be 0 this time around.
It can be 4.
So the trick for finding the y
Just
asymptotes,
divide 5 by 4.
divide 5 by 4. It won't be that actually. Probably the best way of solving for the y asymptote is to see what happens at extreme values in either the positive or negative. Watch this. I'm going to go second table set. Okay. Currently my table is set to start at 0. I'm going to try a very extreme value like 1,000,000.
Where's table set?
Can you guys, so second and then window. Okay. Then when I go to my table, I'm going to see what the graph is starting to do when it's very large. And it's, do you guys get the same thing as I do here?
Yeah.
4.
Mine's starting to be 4 consistently.
Does that mean 4 cannot be?
Now, chances are what's happened here is it's actually supposed to be 3.999999999, and the calculator is just rounding it to 4. Okay. If I do my table set and I go like to say negative a very large number, I'm just going to go to negative like 1,000. And then when I go to my table, do you see how it's at 3.9997?
Why did you go negative and then?
Because what I want to do is I want to see where this graph is kind of getting to in the negatives right here, and where it's getting to in the positives right here. And apparently the asymptote is where y, basically y can't be 4 is the one number it can't be.
But how come it's equal to 4?
Okay, your calculator probably, because I went so far in the distance, it was like 3.9. Eventually your calculator just gave up and said it's 4. But 4 apparently is unsolvable. I can't really give you a great way of finding the asymptote, but I can give you a great way of proving the asymptote is true. Okay? If 4 is the one number that y cannot be, watch what happens when I try to make y 4. So the graph was supposed to be y equals 4x plus 5?
Minus 5.
Minus 5?
And then x minus 2.
Okay, let me try that again. Y was supposed to be 4x minus 5
X minus 2.
over x minus 2. In theory, try making y equal to 4 and see what happens. So make y equal to 4. Then to solve for x, you'd swing the x up to the other side, which would give you 4x minus 8 equals 4x minus 5.
Why did you minus 8?
Because you'd FOIL the 4 times the x and the 4 times the 2.
Your x.
You don't. How would you know?
You see how you have 4x on both sides? Then what would happen is your x's would cancel, and then how could you possibly solve for x when all of the x's are gone? So I don't have a great method for showing you how to calculate a y asymptote, but I can easily check that y asymptote. Does that make sense? Okay. It's actually a calculus skill. We actually learn how to find y asymptotes in calculus.
Like
But-
math.
You don't need to know.
Like Math 31, yeah. I don't need to know how to know it right now. So going back to this guy right here, the asymptote is at 2. The other asymptote is at 4. That make sense? Okay. Let's try another graph. So here we're going to do 3 over x plus 3, and then we're going to minus 2. I'm just going to change my table back to a normal number. 3 over x plus 3, and then add minus 2. You guys get something that looks like this? roughly like this.
Minus 2.
What was that?
The asymptote minus 2.
The asymptote is minus 2, yeah. Yeah. Can I get to that in a second though? You are right there.
Oh, I get that. I get it.
If you're okay with getting this graph, let's talk about what x numbers you can't use. Hopefully it's clear you can't use negative 3. Does that make sense? Because if you tried using negative 3 here, it wouldn't work, so x can't be negative 3. If you're trying to find the y asymptote, I mean, you could do the same thing I suggested. Table set, make the table like start at, say, like a large number, like 1,000, and see what starts to happen. And I've got negative 1.997. What's that getting close to? Yeah, negative 2. That's because of this thing right here. Well, what does a negative 2 do to a normal graph? Pulls it down 2. So if the asymptote on other graphs was sometimes at 0, in this example here, that explains why it pulled it down, so that we had an asymptote here at...
What would a multiple choice question be on this though?
I might ask you, what is the domain of the graph? Or what is the asymptote of the graph? Yeah, usually these ones, to be honest, are very solvable if you know how to use your calculator, right? Because if like I give you a particularly challenging one, because we've still got more to look at here, like you have to be able to interpret and go, okay, what the heck is happening on this graph? Tell me.
So the domain is x can't equal 2, x can't
Y can't equal 2, yeah.
Just because
Yeah.
you-
Another way of writing that, by the way, would be you can go from negative infinity up until negative 3, or you can go from negative 3 up until positive infinity. But like I used curl brackets here, meaning the one number I can't use is negative 3.
Oh,
That's another way of writing it. They could phrase it like that just to mess with you.
I've already forgotten that stupid score.
So like if I use a square bracket like this, it means that you can use the number negative 3. But in this example here, you can't use negative 3, so you wouldn't use those. You'd have to use the curl brackets here.
I understand negative infinity. Why are you negative? Yeah.
Okay, let me try that one more time then. You can use any x number you want, correct? With one exception, you can't use negative 3. So what you could say is you could go from negative infinity all the way up until negative 3. But the one number you can't use is negative 3. So then where do you pick back up again? Well, then you could start at negative 3 and keep going to infinity. But like the way the curl bracket works is you don't actually get to include that number.
Okay.
So this basically says start as low as you want, go all the way up to negative 2.999999999. And then what this says is start again at 3.0111111 and keep going.
Oh, and you can use either or.
Well, you could use either this side or this side. Like both of them are right.
Flat.
The only number you can't use, negative 3.
Okay.
Okay, another one here. I'm just kind of exampling you to death today. I hope you're okay with that.
Sure. We kind of
I think so. It's kind of like an explore, and hopefully you'll figure some stuff out as we just try a bunch of... Like, I'm choosing these on purpose, obviously. So, what's different about this example before I even start? Yeah, it's a quadratic divided by another quadratic. Yep.
Yep.
And yet, it kind of feels similar to start. It does seem like there's a bit of a bigger gap, doesn't it? Let's get to that in a second, though, if that's okay. First, let's talk about what numbers we can't use for x. And it clearly, on my graph here, seems to be there's an asymptote, and I'm gathering it's at negative 2. And if I were to go to my table, I'm going to want to change the table. Why don't I go to negative 2? At negative 2, there's an error. But,
There's also a positive too.
okay, so what happened here?
It's the one because you're squaring it. You can square a negative.
How is there one at positive 2 as well?
Okay, so let's talk about this graph here. X squared minus 4 on the bottom of a fraction. If I wanted to write this, I could write it as x plus 2, x minus 2.
So you can put them
So now there's actually two numbers I can't use. I can't use positive 2 and I can't use negative 2.
So there's a hole.
Okay, yes, you're ahead of me though, but you're right. One of these became an asymptote. The other one actually half canceled. If I were to factor x squared minus 7x plus 10, it becomes x minus 5, x minus 2. So here's what ended up happening. X minus 2 canceled, meaning that 2 is a hole in the graph, but x plus 2 did not cancel, meaning it was an asymptote. So when you draw this graph, it'll look like this, asymptote, this, but we need to make one change here. I need to draw a hole where x is 2 because x cannot be 2 and it also cannot be negative 2.
So are asymptotes and holes kind of the same concept? Like
They're similar in that those numbers can't be used, but they're different in how they make graphs look. Asymptotes make the graphs have like very swoopy looking sections to it, if that makes sense. Whereas you won't even notice a hole in the graph on your calculator. Like as I look at this graph right here, I don't see a hole in the graph, right? Unless I actually go to the table of values and then it shows up.
So only one is the asymptote.
So one of them is the asymptote and one is a hole in the graph.
I don't
And that's
understand.
NK. Which one is which?
Which one is which? Yeah.
Okay.
So the reason why 2 is a hole in the graph is because the x minus 2's cancel. The reason why negative 2 is only an asymptote is it had no one to cancel with.
Okay, so the x plus 2 bracket, like that section.
Yep. This guy right here,
That is our asymptote.
yeah, let me write this out here. This guy caused the asymptote. That guy caused an asymptote. Whereas the one that canceled caused the hole. Okay,
Are these-
either, sorry, go ahead.
Are these gonna always factor down so we can indicate which one is which?
Sometimes they will, sometimes they won't.
How do you indicate which one's which?
You'll have to check and see whether it does factor. Like some things, yes, they will factor. Other things, they won't.
So if it won't factor, then you're not gonna get
Probably.
two different ones?
Yeah, probably not.
Okay, so it'll be pretty, not obvious, but you'll be able to tell.
This is where I think I know where you're going with this. I can't give you rules that always work. I'm sorry. This is where it depends on what is on top and what's on the bottom. Because like sometimes it factors, sometimes it doesn't. Sometimes it cancels, sometimes it doesn't. I can't guarantee anything really.
If it factors in, you can cancel. The ones that cancel will become a hole.
Yes.
The ones that don't, you can cancel.
Yes.
So, our whole, what's our whole? Our whole is
Oh,
2.
yeah, our hole, that's a good question here. The hole is at 2 comma what? So how do we find that hole? Oh,
Because
sorry.
x minus 2, that's because it cancels, x minus 2 cancels, you know that that's a whole.
Yeah.
So is it minus 2 or is it 2?
Well, 2 is where the hole is because 2 minus 2 is the one that
Okay, so
canceled?
it's 2 on the x-axis.
Yes.
There's a hole.
Yes. So for x is 2, there's a hole in the graph. My question for you guys now is where's the hole for the y then? Well, now that we've canceled out the x over 2, can I plug 2 into the remaining stuff? So the leftovers is x minus 5 over x plus 2. If I plug 2 in for this, I get negative 3 over 4.
So it's not 0.
So it's not at 0. Your hole in the graph is at 2 and negative 3 over 4.
And our asymptote is x cannot equal negative 2.
So yeah, so we have an asymptote where x is negative 2. We have a hole in the graph where x is positive 2. We have a hole in the graph where y is negative 3 over 4. And by the way, there is still a y asymptote somewhere. So let me go back to this graph here. To find that y asymptote, again, like change your window settings and just make it a fairly large value and see what's happening. And it looks like it's getting fairly close to a y value of 1. And double check that in the negatives just to make sure. It doesn't take long to double check. Negative 1,000. Well, okay, so it means that one side is slightly above 1 and one side is slightly below 1. Does that make sense? Like this side is coming down on 1, so therefore it's slightly above, And this graph right here is getting slightly larger going to 1. So here's how we need to write this then. Your domain, x cannot be 2 and negative 2. And your range, y cannot be 1 and negative 3 over 4. And these are for very different reasons. One of them is because it's an asymptote. The other one's because there's a hole in the graph. And then same thing for the y value. One's part of an asymptote, and one's part of a hole in the graph.
So the one that is, well, I guess that's pretty obvious, is the one that's part of the hole in the graph. You have to calculate with that specific x value. So that's
Yes.
pretty obvious.
Yeah.
Okay.
So
Is the only way to calculate those y asymptotes is to like put it in your.
that's the best way I have for you guys to do right now. It's not the only way, but it's a calculus topic, which we'll get to later. So
There's no
this is
crazy-
much more efficient.
Algebraic,
There's not a better way of doing it with what you guys know how to do right now.
and they're not going to be tested on it.
No. No.
Oh, thank goodness. That's
So, because here's the thing, you can always test that as well, right? Like if you want to confirm your answer, say 1 needs to equal x minus 5 over x plus 2. Then when you times this guy to the other side, you'll get x plus 2 equals x minus 5. Your x's will cancel, and you'll now have proved that when y equals 1, it's impossible to solve for it. So you can confirm a y asymptote easily, but without using calculus, you can't really find it easily. So. Okay, why don't we read this slide here, then we'll take a break for a bit, because I feel like some of you guys are getting a little distracted. Here's a summary then of this last slide, because I need you to know this. This comes up a lot. The two things that you typically will have are an asymptote and a point of discontinuity, which is the hole in the graph. Okay. In this example right here, the reason why there's a hole in the graph is because it factors to x minus 2, x minus 3, and something cancels. So if something does cancel, it just puts a hole in the graph. Your calculator will not make it appear that there's a hole in the graph. So you really got to keep your eyes open for that. Because upon first glance, your calculator will not obviously draw a hole there.
But if the x2's minus cancel, shouldn't it be a negative 2?
Positive
No, because the positive 2 is the one number you couldn't use.
Okay.
And then when you plug 2 back into the remainder, 2 minus 3 gives you the negative 1 for the y hole. For this particular one right here, I don't know what the equation was, but I can tell you that the bottom of the equation must have been x minus 2. The reason why I know the bottom of the equation was x minus 2 is because I have an asymptote at 2. I don't actually know what the top of the equation was, but I know for sure the top of the equation, though, did not have x minus 2 in it. Otherwise, it would have canceled. So, like, I don't know what the top of the equation is. I'll just call it A. But for sure, the bottom is x minus 2.
Okay, I just have a question.
Yeah.
If you say that the top of it couldn't have been, you say the top of it couldn't have been x minus 2 because it would have canceled and
Yeah.
that would have left you with an asymptote.
It would have left you with a hole in the graph instead then.
Oh, I'm mixing things up.
Does that make sense?
I'm mixing things up.
So I know the one thing the top of the fraction wasn't. That doesn't help a lot, though. That makes sense.
And do we need to worry about the y asymptote in this context?
That doesn't, like, I mean, the y asymptote is 3, but that doesn't necessarily tell me what the graph was necessarily yet, right? So, okay. So far, so good? Okay, go take a 5-minute break. We'll finish the rest of the examples in a bit. Okay, let's try this one here. I got one last example, and then I'm going to show you some more typical questions. Okay. So this guy right here involves a quadratic again, but now it's just 3 divided by x squared minus 10x plus 25. Before I press graph, I'd like to start suggesting that if you can factor, we should probably start doing it now. X minus 5 twice? Well, it means that if x minus 5 is there twice, what's the one value I can't use for x? 5. So I should hopefully have like something happening where x is 5. Let's see. Now the graph looks slightly different. Okay, well, first of all, is there an asymptote?
5.
Yeah, I think if I were sketching this, it almost looks like a volcano. It goes flat, comes up, comes back down again. And so there is an asymptote here at 5.
Pretty good.
Okay, now that being said, where does the range of the graph not head to?
Into anything that's negative.
Anything that's negative,
Oh yeah.
right? Does it not appear that right off the bat that this graph does not go below the x-axis?
Why did our graph, because like our calculators draw the asymptote, why didn't it just on this graph?
I don't know why it didn't on this one. Oh, I do know why. Some calculators, the way they draw graphs is like they literally go like up like this, then they have to continue drawing. So like they can't lift the pencil off the paper and they keep going here. But since this one went like all the way up, it could then keep coming all the way back down and didn't actually draw it. It's just kind of like the way your calculator draws. It's like an Etch-a-Sketch where it like it has to like go. Does that make sense?
I got you.
Okay.
So x cannot equal 5.
Okay, so x can't be 5. What about y though?
Greater than 0.
Good. Now can it equal 0?
No.
No.
Why not?
Because you can't divide by
Because
here.
that is the asymptote.
That is the asymptote. Yeah, there is an asymptote here. So guys, this would be my first example of one where the domain and the range were different than your asymptotes. Your asymptote is y can't be 0. But your range is y has to be greater than 0 because you can't have negative numbers. This graph just apparently doesn't work that way.
So, but then your domain is the same, right?
Your domain though would just be x can't be 5. Like you can have any other x number you want, you just can't use 5.
So how do we figure out that y can't equal 0?
Well, I didn't actually do it, but we'd go second table set, take a look at the table, and do you guys remember like e to the minus 6? That means like 0.00000003.
Okay, so it'd be like 1.
0
Or
basically.
0.
Yeah.
Is
Essentially
that
0. Apparently no.
Yeah, pretty much.
Remember? Yeah, like what?
No, the 0. Okay.
Yeah.
That makes sense so far? Okay. Long story short, guys. Gosh, Kayla. Okay. Long story short, all of these graphs are going to look quite different. Okay. I can't really give you a hard and fast set of rules and says, if this graph looks like this, here's why. But I can give you a couple of pointers. If you can, try factoring. Okay. If stuff cancels when you factor, you get holes in the graph. If stuff doesn't cancel, the bottom becomes an asymptote. Everything else, it can't tell you. Okay. So here's some typical examples of, you know what, I'm going to come back to this slide. Remind me, okay? Here's like an example of a question I might ask you. It could be like a matching question. Match these 3 graphs. But I'd like you to try doing it without using your calculator. Okay. So for example, this guy right here could be x squared plus 2 over x minus 2 x plus 1. Can anything cancel in this first equation right here, the k of x equation?
No.
Okay.
Okay,
So
well, how did we get minus 1?
Then
That-
you know you're gonna have 2 asymptotes.
this guy right here. Okay, so that's where I'd go next then. We need a graph then that has 2 asymptotes.
In x, anyways.
And those asymptotes would be at 2 and negative 1.
What's the third one?
Yeah, so this guy right here is k of x. This graph right here is x minus 1 over x minus 1 x plus 1. So something does cancel. So where would the hole in the graph be then?
1.
At 1.
Graph 1.
Yeah, this one has a hole in the graph at 1. It also, by the way, has an asymptote at
Negative 1.
-1. So this guy right here would have been L of x. Ready?
So is it like fair to assume that like if it's divided by a quadratic, it would generally have
What's L?
I really don't want to say anything along those lines because it depends. If it's a linear divided by a quadratic, it'll be different than a quadratic divided by a quadratic or a cubic divided by a there's too many possibilities. Does that make sense? Like I think you might see some patterns going after a while, but I think that's a dangerous habit to get into because I'm gonna try to find you guys some other weird looking graphs, and Does that make sense? I'm sorry, I know you want to look for patterns. You might find some, but I guess by default this guy here is m of x. But let's just confirm this is x squared minus 5x plus 6. You can factor that into x minus 3, x minus 3.
Two.
Minus 2, thank you.
So would that mean x plus?
Wait a minute.
Now, can these guys right here, can x minus 3 and a 3 minus x, can they actually cancel each other?
Isn't that x plus?
Unless you can't factor over something.
Okay, so I want to show you guys a trick here. If I give you x minus 3 over 3 minus x, what you can do is factor out a minus 1. So like, say this guy right here on the bottom, you can make 3 minus x the same thing as negative 1 x minus 3. Because if you do negative 1 times x, you'd get negative x. And if you do negative 1 times negative 3, you'd get positive 3. So it is possible, actually, that it may not look like it can cancel, but this guy actually factors to negative 1 x minus 3. And so there is a hole in the graph at 3. Do you guys see how there's a hole sitting in there? It doesn't show up very great on this one here, but there was a hole on this one. So what I might do for a multiple choice question, I actually probably would make it numeric response. I'd give you 4 graphs, and I'd have you like match them and say like this would be graph 4, this would be graph 2, this would be graph 3, and like I'd actually make you like do numeric response. So that's the way I can phrase it.
And there's no asymptote for this.
On this last one here,
Yeah.
no, because this canceled,
Okay.
and so there's nothing left on the bottom to be an asymptote.
So if it cancels, it's a hole.
Yes. Why don't you guys try these ones then? Try matching these 3 graphs up, and try not to use your calculator, unless you have to.
Can you factor x squared?
You can take x out.
X bracket x plus 2. Are you talking x squared plus 2x?
No, I was talking x squared plus 1.
X squared plus 1 you can't factor, no. Sorry, we weren't on the same page there.
Are we doing?
Bertie, you asked me a while ago about like some pattern type stuff here. You might notice that graph 1 and graph 3 are a couple of graphs that I haven't even shown you those ones yet. I know, and that's the point I want to make, is that I can't give you a pattern. Like each one is going to be weird and different on its own right. Like graph 3 is very weird. Like it like goes halfway up to 4 and then it just comes back down again. Like why?
Factor the top with a net.
Yeah, you can take out a x.
Oh,
So if you guys are on A, you can make it x bracket x plus 2. And then on the bottom, you can take out x minus 2, x plus 2.
But can the x plus 2 and the x minus, or x plus 2 and x plus 2 cancel?
Yeah, so that's a hole in the graph.
So shouldn't they be at 2 though?
No, the hole should be at negative 2. Because this thing right here, what number can't be used in an x plus 2? Negative 2 can't be used in an x plus 2. The factor is x plus 2. Therefore, the root is negative 2.
The factor is x plus 2.
So like the hole in the graphs when x plus 2 can't be negative.
Yeah, so the hole is at negative 2, and the asymptote is at 2. Which graph fits those parameters? Which graph has a hole at negative 2 and an asymptote at 2? Graph 2 does.
Please excuse the interruption. Ethan Greer, please come to the office. Ethan Greer to the office, please.
You can't factor x squared plus 1 into x plus 1.
You can't factor x squared plus 1 at all.
Oh, yeah, that'd be.
why can't you do x plus 1 and minus 1?
That's a difference of squares, and that requires it to be x squared minus 1, not plus 1. Just so you guys know, this graph right here, the one on the bottom that doesn't factor whatsoever, there are no holes in the graph or asymptotes for this one, because the bottom of this fraction can never be 0. How would you ever make x squared plus 1 equal 0? If you used a positive number, it would just make it more positive. If you used a negative number, it would make it actually positive again, right? Because you'd be squaring. So this graph right here, by the way, was the b of x graph. Like there were no holes in the graph, there were no asymptotes.
You can't factor x squared.
You can't factor x squared plus 1. By default, that makes this one c of x. And to prove it, it would be 2x over x plus 2, x minus 2. Since nothing cancels, you must have two different asymptotes.
So how can we tell that graph 3 would be this?
This one right here? Based on these three, there were no asymptotes, and there were no holes in the graph.
Okay.
Because like this bottom thing right here didn't factor, so there was no reason why there would be either a hole in the graph or an asymptote.
Okay. And then the reason why you could see that there's no asymptote is because obviously the graph shows no asymptote.
Yeah, like this graph right here doesn't show an asymptote anywhere. Quick question I want to give you guys then. If I were to give you this graph right here, this 2x plus 4 over x squared plus 1, and I were to ask you to find the range of the graph, how would you find the range of this graph right here? Let me type it in your calculator.
Less than.
2.
We find the maximum.
Yeah.
Yes, there we go. Thank you. You'd find the maximum value. You'd have to find out how high it got to.
What did you just say?
Okay, if I were to give you graph B,
Yeah.
which looks like this, just bear with me for a second while I graph it. So here's graph B. Okay. If I'm trying to find the domain looks like you can use anything for x. There's no problems with the domain. But if you want to find the range, you're going to want to find the maximum value to figure out how high this graph truly gets. And it looks like it gets as high as 4.236.
So y has to be less than or equal to 4.236.
So like the highest value for y must be 4.236. What's the lowest value for y? Well, I gotta check and see what happens as this graph keeps going along here. I could go to my table. And like here it looks like it's negative 0.02, but I may need to like look in between there because this graph does some weird stuff. I might make my x values go to negative 20. I just want to see what this graph does over in this direction here.
Stay along.
Do you guys see how it goes into the negatives here though somewhere? Somewhere down there there's like a minimum value. So I might try like minimum instead.
I thought it doesn't have like asymptote.
Like I think what it's doing is it's going down below and then it's coming back up. So it's almost like it's doing this below the axis and then it's leveling off. And somewhere in here there's a minimum value. So if I try to find a minimum, I'm just going to take a leap of faith and hope there is one in there somewhere. I'm pretty sure there's an asymptote at 0 here though. It gets as low as negative 0.236 apparently. So that's as low as this graph ever gets.
Whoa, what did you?
I did a minimum. You know how like maximum would find me this top height? I did minimum to find me this lowest value.
How? Like, where did you left side?
I went really far on both sides to just make sure that I caught it in there somewhere.
We can't even assume that it necessarily just goes on forever.
No, that's one of the issues here is that like this particular graph was kind of odd looking, right? Like the graph did, like it looks to me like the graph is asymptote, goes down a little bit, comes up, and then comes back down a little like that. So I got negative 2.236 is as low as it gets here.
What if it goes lower on the other side?
I don't think it does, but it wouldn't hurt for me just to check my x value and just make sure. But I'm pretty sure as I look at like my table, like this is where I can't give you hard and fast rules again. Like I can say, you have to like explore it yourself. And say, okay, well look at your x values. They're getting smaller, smaller, smaller. I don't think they're ever getting into the negatives though.
Then y has to be greater than.
Does that make sense?
Or equal to.
Y can be from negative 0.2.
So here's one way of writing your range.
Would it include that?
It would have. Yeah, you're right. Sorry.
Attention please. If anybody has found a wallet, it has a British flag on it, red, blue, and white. Please bring it to the office, no questions asked. If you found this wallet, again, please bring it to the office, no questions asked.
And
You stole it, we won't.
that needed to be brought back like right now. Okay, I want to go back a slide. I skipped one here. I want to show you two graphs. These graphs have almost the exact same equation.
Wait, square brackets means you can't include them, right?
Square brackets means you can include the values, so that should have been square brackets.
Okay.
These two graphs, you might notice, are almost the exact same.
Just a plus and a
But this one's a minus, that one's a plus. This one here, apparently something cancels, and it makes a hole in the graph. This one here, apparently it doesn't cancel, and it makes an asymptote. Here's the point I want to make here. There is a huge gap from here to here in the range of this graph. That's also possible. So you may need to actually find the minimum value right here and the maximum value right here in order to figure out range.
Does that mean there's more than one y asymptote?
There actually is no, technically there's no asymptote in the y direction here. There's just like a big like gap in the middle of your graph. It's like your graph does this and then does this, and like everywhere from here to here, there's like no values. But it's not actually like an asymptote in the same way. So you just have to find what those two numbers are. Okay, one last example, then I'm calling it a day here. Here's what I'm going to expect of you guys on like a test question when you guys write a quiz. So I'm going to say a rational function consists of a linear function divided by a quadratic function. Guys, a little more focus, please. Thank you. I'm almost done. Okay. I'm going to tell you there's an asymptote, and I'm also going to tell you the point of discontinuity. I want you to write me the equation of the function. So we're going to work backwards. I'm going to give you some of that critical information, like where the hole is, where the asymptote is. And your job is to get me the equation. Okay. I've seen this question on the diploma, actually. They didn't phrase it quite like this, written response question, but they have asked it similar before. Okay. So let me walk you through how to solve this. If there is an asymptote, what does that mean? Okay, it means that x minus 3 then was on the bottom of your fraction. If it's an asymptote, should there be an x plus 3 on the top as well? No. Good. Okay. If there's a point of discontinuity at 1, that means that x minus 1 was on the bottom and was on the top. Does that make sense so far? So this guy contributed to the asymptote, and both of these guys contributed to the whole. Well, here's the thing though. Are we sure that that's going to make the point of discontinuity be at -4? Just like with other equations that we've solved, there is the possibility of a leading coefficient still being there. Does that make sense? So it could be like 3x minus 1 over x minus 3, x minus 1. So we need to find this leading coefficient, just like we always did in other questions like this.
But like -4 or y?
Perfect. We're just going to plug in -4 for y. Now, should I try plugging 1 in with the equation looking like this, though? I can't, can I? So, okay, so I will cancel these guys and do this. -4 equals a over 1 minus 3. -4 would equal a over -2. So my a value would be 8. So now my equation would be y equals 8 x minus 1, that's a linear equation, over x minus 3, x minus 1, that's a quadratic equation. I really can't check this in my calculator all that well, but hopefully it meets all the definitions I'm looking for. There's going to be a hole in the graph where x is 1. There's going to be an asymptote where x equals 3. If I did cancel these guys, y equals 8 over x minus 3, if I try plugging in 1 minus 3 would give me -2. 8 divided by negative 2 would give me a y value of negative 4. So this would have been my equation. Or on the diploma, they probably would phrase it like this. What would that be? Minus 4x plus 3. Where I foiled it out. The one year they used this example, they actually made it numeric response, and they wrote it like this. This was particularly mean. It was y equals ax minus b over x squared minus cx plus d, and they asked you what are a, b, c, and d. I know, that was mean. Given the stuff up there,
Because
right?
that means that like you. Oh.
Because what they didn't want people to be able to do was just type graphs in their calculator until they got one that worked. They wanted people to actually solve it. So they made a numeric response. They gave you the basis of it, and then you had to figure out what A, B, C, and D were.
You don't give us questions like that.
I want you guys to be able to solve that. Well, I mean, they could ask. I mean, this is a challenging question, don't get me wrong. But I think with a little practice, you guys will have it.
Okay, so with the point of discontinuity, it gives you the 1 and the negative 4. So the 1 tells you that that's where your hole is, so it's x minus 1.
Yeah, because then 1 minus 1 would be 0, which means we can't do the 0. That make sense? Okay. Okay, that's kind of it for today. Tomorrow I'm going to give you one more lesson. Tomorrow's lesson is actually going to be a review of what we did in grade 11. I'm going to give you a whole bunch of rational functions, and we're going to try to solve them for x. So something like this, or this, or this. It's going to be a complete review of grade 11. Like I did this in grade 11 a lot, knowing that we'd have to do it this year a little bit more.
Wouldn't that turn into like a quadratic function?
Yeah, it eventually turns into quadratic sometimes. So that's our goal tomorrow. And then on Thursday, I'm going to give you your assignment. Okay. So in the meantime, here's some questions to try. You probably should try a couple of them, okay? Don't do nothing.
What?
I know. Okay, any questions, guys? Okay. The last one there, 451, 4 to 9, those are probably the best ones to start with. Yeah, those are the ones on what we did today. The questions basically are all about graph the question, find me the domain and range. And so, like, as many functions as I showed you guys, there's even more out there that I'd like you guys to look at.